Okay, Bismillahirrahmanirrahim. Welcome back to Low Level Programming again. And now we're going to be continuing where we left off, and we're going to be discussing repetition now. Just a quick recap. So far, we've seen how different programming structures, such as your taking input, performing arithmetic operations, taking the negative value of a particular variable, are handled through low level programming. And we've also handled selection statements and how the conditional jump is used with respect to your low-level programming language. And now we'll move on to see how different types of loops can be implemented using low-level programming. Now, as you can see here on the left, there is this code written in, it's written in pseudocode, but let's just say some high-level language. And as you can see here, that there is a repeat loop being used here. So repeat loop is post condition. So that means is that this loop will run at least once, and the condition will be tested. If the condition is not yet met, then I will jump back over here. Now I'll repeat that. I'll start my loop over here. I'll run these two lines, and this condition will be tested. If this condition is not true, which means that a is not equal to 5, then I'll jump back to the start. If a is equal to 5, then I will not jump. I'll move on to the next line. So again, this is with reference to what happened in the previous topic in FS, that I am making a decision on when to jump. Am I jumping based on something being equal, or am I jumping based on something being not equal? In this case, how is the jump? By the way, any disturbance of the normal execution of your code, which means a normal sequence. If any condition causes the normal sequence of the code to be disturbed, so I'm executing one line after the other. If I can't do that for some reason, and I have to skip lines in between, that is known as a jump. That skipping can be downwards, as well as I can have to go back upwards as well. So what that means is that if I am disturbing the normal sequence of execution, which is top to bottom, it will be referred to as a jump. So in this case, you can see here that I'm jumping. How? By going back to this place. And why am I jumping? If this is not equal to 5. So if we remember that the repeat until condition means that if the condition is not true, I will go back and run the loop again. However, if this condition is true, I will exit the loop. No more running. So what will this condition be true on? It will be true on if a is equal to 5. So if it's not equal to 5, then I am jumping back up here. So it should make sense that I'm using JPN, jump if not equal to, because I'm jumping back if a is not equal to 5. Okay. Now let's look at what happens in assembly language. We are initializing the variable a with the value 0. We need two lines for this: LDM hash 0, STO into a, store into a. So we studied this before. Initializations are handled this way. A simple line for initialization has to be written in 2 lines in assembly language. Okay, a label. I am using a label to show the start of my loop body. If we were using a high-level language, we will see keywords such as while, repeat, for, stuff like that. So we're making that prominent here by the keyword, not the keyword, but a label loop. I have entered this myself. It's not any sort of reserved word. It's just a simple label that points to this address being the start of this loop body. So it says output asterisk. So what we're doing here is that I'm going to load using immediate addressing the number 42. 42 is in my ACC. I will then go ahead and run the out command. Now, if you remember, what out does is it simply prints the character for which the ACC is already for which the ASCII is already loaded into the ACC. So in this case, I am printing out a character whose ASCII value is 42. Yes, it is. That means I am actually printing out the asterisk. So the ASCII value for the asterisk is 42. Similarly, the next line says that I am to add 1 to A and then store the result back to A. So if you remember, this is basically incrementing the counter. And often in your exams, in fact, probably all the questions where you are required to implement this into low-level programming, this statement, you will require these 3 lines: load A, increment ACC, and store it back into it. You will require these lines. And these lines they contribute just 1 mark, because it's understood that an incrementation process cannot be completed without these 3 lines. You have to add these 3 lines. So for these 3 lines, you are awarded 1 complete mark. So if you miss any one line here, that mark is gone. So this is how we increment a counter. After incrementing the counter, the value is still in ACC is still loaded with A. I will compare the value with 5. Compare the value with 5. You can see here I'm comparing an actual value with 5. So this is immediate addressing. I'm comparing the value of 5 with the contents of ACC. I'm comparing the value of 5 with the contents of ACC. If they are not equal, then I'll jump back to the start. So if they're not equal, I'll jump back to loop and start all over again. And each time I pass by here, I compare the contents of ACC with 5. And if it's not equal to 5, then I'll jump back over here. As soon as this comparison results in both values A and the ACC being the same, in which case I will not jump and I will simply progress to the next part of the whole program. Now, this is an example over here. Okay, for this, we will first have to load #1, store it to number. So assigning something with a value is quite simple. Simply load that variable. Load the immediate address using 1, store it into that number, that address. Then, as you can see here, I'm loading using immediate addressing 0 and storing in total, loading 5 and storing in max. Afterwards, when I start the loop, I'll load the total, add number to it, store it back in total. I will load a number, increment ACC, store it back in number, and then compare it to max. If they are both equal, then I will not jump. I will jump because if they're not equal. So JPM loop back over here and start all over again. So very simple. Now, another state in a feature that your low-level programming language should be able to accommodate, and that's also taken from high-level languages, is taking an input and output. Now, if I want to give something as an input, now if you remember, the in command only does what? That it takes the ASCII value. So if I run the in command as we're doing over here, user is expected to press a button, and the ASCII value for that key will be placed into the ACC. So if I want to use a numeric value, the actual number, and the user enters a number from the keyword, the ASCII value for that number will arrive in the ACC. So if I want to use the actual numeric value, I'll have to make some adjustments for that. We'll look at an example. So for example, in the first line is saying input A. So you're just asking the user to input something, and whenever it inputs, it will go into A. So I will simply run in, the user will give some input, and whatever input they gave will be stored in A. Simple as that. Similarly, if I want to output something, output B. Now, this is a little different. What's happening here is that if you remember, LDR does what? It assigns a value to the index register. LDM uses immediate addressing to load into the accumulator register. LDR uses immediate addressing to load into the index register. So what I'm doing here is that I'm loading my index register with -1. After that, my loop will start. I will increment my index register I will load using index addressing from my B, print it on the screen, compare it with hash 13, and if not equal to, then I'll jump back to loop. Now, let me explain what's happening over here. Assume that I have this line written here, like this. This is one line, right? So my output B is going to output this line. So as I just mentioned a little while ago, LDR is immediate addressing using LDR hash -1 means using immediate addressing load the value of -1 into my index register. I'm going to draw my index register here. This is my index register. The value of the index register is -1 at the moment. This is my IX. And this is my A. This is the string I want to print out. This is currently in B. Okay. As you can notice that this is a string, and this string obviously has different letters. And at the end of the letter, when it has a line, for example, this whole line, and this coincidentally, this entire line has just one word in it. Now, how do I know that when I start reading from here, how do I know that I have reached the end of my line? How do I know that? Well, I know that because at the end of this line, there is a character known as carriage return. Now, carriage return is basically the equivalent of your enter key on your keyboard or the return key on MacBooks and Mac PCs. There's a return key on the keyboard. Now, what does return do is that causes your, so for example, if I've written something here, and as soon as I enter the return key, you notice the cursor now starts back over here. So not only did it move to a new line, it moved to the start of the new line. So that's what the carriage return does. Now, this is my string that's currently loaded in B. This is my index register at the moment. And as soon as we begin the code, begin our loop, the first thing it says is that increment IX. So, okay, if you so, we'll do that. We will increment the IX. So now my IX should be at 0. And that's what happened. After that, I will load using index addressing. So load using index addressing from where? B. Now B is my base address. This is my B. B is starting from here. B is starting from here. Now think of this whole string as an array. And at each array position, I have different letters here, including the carriage return. So at each position, I have different letters here. So I am loading using index addressing. So it says, if you go to B, and these are the consecutive, you can say that it's like this. First position has H in it. Then it's got the second address has L, E, L, L, O. And this is the starting position is B, like so. Okay, this is B. So if I print B at the moment, the contents of B actually be printed on the screen. Okay. So let's just say I'm trying to print this entire string, and I have got carriage return over here as well. This is carriage return. It's an arrow. Carriage return. Okay, I'll start off by increment IX. So my IX is now 0. I will LDX from B. So by the way, B is right here. And if I add the index register value, which is 0, I'll come back right here. So that means now my ACC will have, this is my ACC over here. ACC after this line will have H, capital H in it. Or not exactly H, but the ASCII value of H. After doing that, I will run the out command and the letter H will be printed on the screen. I will compare the current ASCII value with the carriage return. If it's not the carriage return, that means I have not yet reached my end of the string. So since H, I just printed H, and my character is not actually equal to #3, then that means I have not reached the end of the line. So the next character I will read is E. How will I read here? Because first of all, I will increment my IX. This time my IX will have 1 in it. So after I do index addressing, that means B plus 1. So that means I'll move 1 place down, E. So because of that, my ACC will now have E in it. I will print it on screen compared to #3. It will not match. So that means I'll go back up and do it all over again. Increment the AX to 2, LDX to 2, L will come in the screen. And then same thing, index 3, L will come on the screen again. Finally, index position 4 and 0 will come on the screen. And at the end, when I do, I'm still, my ASCII value for 0 or O is still not 13. It's not the carriage return, in which case I'll move on 1 more place. And this time my IX will be 5. And I will read, my ASCII value will have this carriage return character in it. If my carriage return character is equal to 13, which it is, I will simply, this is not equal to, it's equal to, I will simply exit my loop and move on from here. So what I did is that I treated my entire string as a string of characters. And this way I'm capable of moving through these characters using this. So second thing, whenever you will notice that we're using arrays, we will use index addressing there. So index addressing is paramount whenever we're working with arrays. Okay, next example, look. What I do is I will input A. I have loaded your index register with -1. I will start my loop, increment my index register, exact same the way we did over here. The difference is, instead of loading using index addressing, I'm storing using index addressing. So basically what that means is that if, say, for example, I understood what's happening over here, and I'm reading a whole sentence if I must, without reading the carriage return, I'm reading a whole sentence. So this is what this assembly language does. It reads the whole sentence. Similarly, I may want to may want to save a whole sentence or a word or multiple words as well. In which case, I will use the same technique of looping through your index positions till I have satisfied the position and I've not reached the end of what you call it, or the carriage return. If I have reached the carriage return, that's the end, no more jumping. So in either case, if I'm entering data, I'm still looking for the carriage return. Or if I'm printing data, I'm still returning for the carriage return. Or if I'm entering data over here, I'm still looking for the carriage return for the end. So say you're inputting a string, you will finish it up by entering by pressing the enter or carriage return button at the last. So let's check out this example.